So in this video we're going to talk about thin film interference. Okay, thin film interference, it's a little bit of a complex kind of concept in terms of getting your head around what's actually going on when light interacts with a thin film. So most people have seen this but not realize what it actually is. So oftentimes when you create a bubble or something like that, you'll see that shiny appearance. You see it a lot on like fuel forecourts where you're getting fuel, where there's been spilt petrol. You'll see it's kind of shiny and it gives off all those pretty colors. Well, that's all caused by thin film interference. And hopefully maybe in class you might be able to blow some bubbles and see thin film interference on the surface of those bubbles as a result of light interacting in this way that I'm going to show you here. So what we've got is, for thin film interference to occur, we have got a situation where you've got light is coming from air. It may not be coming from air, but for all intents and purposes, most specifications take it coming from air. It's very unlikely you would ever get a question not involving air, but we might make another video just showing more advanced concepts about what happens when it's not in air, and I'll mention that later. But, and then say we've got like an oil layer here or something like that. That might be your fuel, or it might be your solution. And we're going to talk about what happens when light comes in and effectively reflects off these surfaces. So what happens is, as light comes in, so this is my ray of light here. And what, as you can imagine, any light that approaches this surface here will undergo either like a partial reflection and will also refract. So it will slow down, its wavelength will shorten, etc., etc. Especially when it goes from a low refractive index of 1 to, let's say, a refractive index of 1.3 or something like that. So what we have here is we have a situation where we have a light ray coming in and it reflects off this surface here. I'm not going to draw it on top of this one. I'm just going to draw it to the side, so a light ray will reflect off of it. So this is a reflection that occurs here, so reflection. So that light ray reflects off there. But obviously that is a partial reflection. You get some light that carries on straight through. And that light will will partially reflect as well. And so we get our partial reflection here that will then come back out. And obviously this could happen a couple of different times. And depending on what happens, how many times it happens, depends on what happens in terms of destructive or constructive interference. We'll come back to that in a second. But one thing you do need to be aware of, we're going to call this distance here D, okay? Because that distance is important. That's the thickness of that thin film. That's right there. One thing that might be important to note is that this could be air, or it could be another substance on the other side. If it is, it will have very specific consequences, and we'll talk about what those consequences are here in a second. So as you can imagine, if we've got a reflected ray here and a reflected ray here, depending on how thick this is, depends on what the phase difference of these waves are when they leave here at this point here. So for example, they could leave completely in phase. As a result, they would constructively interfere. So this wave could leave like that, and the green wave could leave exactly the same, and that would be constructive interference. But what if the distance has caused this to then be out of phase? So the distance could cause this to be out of phase, which causes the blue one to maybe be shifted by pi or 90 degrees. Or sorry, pi is 180 degrees, be shifted by 180 degrees. So what happens is that we get that by the blue, and green is still the same. So as in this result, we get destructive interference. And that's all dependent on this right here. Whether or not this distance is going to cause the reflected ray to be 180 degrees out of phase or in phase. Obviously, you might have variations thereof. This might not be an exact proportion of it, but for all intents and purposes, you're going to get one of these two conditions, constructive or destructive. Well, bear in mind, it's all to do with path difference, and the path difference is not just d here, it's 2 times d, because it's traveled an extra distance. So the path difference in this circumstance is equal to 2 times d. And what's important to note is that path difference is going to either equal to the criteria for constructive interference, n lambda. Remember this, go back, have a look at this when we looked at interference. When the path difference is n lambda, it means that the waves are still going to arrive in phase and so be constructive. Well, what happens if that equals to the destructive section? Well, how much has this been changed by? Well, it could be n plus a half lambda. Now, we're going to have a little bit of an issue here, aren't we? Because look here, we've got n for our number of wavelengths and n for a number of wavelengths here. And we've also got n for our refractive index. So what we're going to do is we're just going to change this letter not to n, but to an m. Because oftentimes we can trade those out for different letters, because this is just the number of wavelengths, whereas this is a specific value. So we're going to leave refractive index as n, and we're going to change this letter to be m here, so we don't get too confused. So depending on whether it's the path difference here is equal to m lambda or m plus a half lambda, depends on shows us whether we get constructive or destructive. But there's another thing that you have to consider here, and this is what makes things a little bit more challenging with thin film interference. There's a specific criteria about these waves that can cause them to undergo a 90-degree shift when reflecting off these boundaries. Okay? Now, you can kind of almost imagine this 180-degree shift as when you might put a string against a wall, for example. So if you have a string attached to a wall or a spring or something like that, when you move that wave across, when this wave comes here, when it reflects, the reflected wave goes back the opposite way. And that is a very unique feature that happens. And what we can say, look, that's how much has that been shifted by? That's been shifted by pi, or 180 degrees. And so as a result, this same thing can be observed sometimes here, where when a wave is reflected, it can shift by 180 degrees or pi. Well, that causes a huge problem, because if that happens, that can cause these two criteria to flip. So if a pi shift occurs, then this is going to be destructive, and this is now going to be constructive. Well, that's awfully confusing, I know. But it's something you just need to remember, that sometimes the reflection occurs. Well, you might be asking, well, how will I know? How do I know if a reflection causes a pi shift that causes it to flip around? Because remember, if we flipped this now, so if this wave was flipped by 180 degrees when it was reflected, this wave that was constructive would now be moving in a destructive pattern, and opposite way round for this one. So like I said, this will now be constructive and this will now be destructive, where it was constructive and destructive before. So, to answer the question, how do we know if a pi shift occurs? Well, it's actually a very simple concept and just a nice little rule that you can remember, that this kind of reflection, this pi shift occurs when going from a low n to a high n, or higher n, I might say. So in the case of air going into oil, what we get here is we get a pi shift, because it's going from low n to high n. We're going from 1 to 1.3. And so we have a pi shift occurring at this reflection. So this is pi shifted. But look, there's another reflected ray. Well, let's look at our criteria. You get a pi shift when you go from low n to high n. High n back to air. Well, remember, air is just n equals 1. So there is no pi shift here. That's important to note, because if there'd been 2 pi shifts, well, at that point, then you've got a problem, because you're just going to go back to the original circumstance where m lambda was constructive and m plus a half lambda was destructive, because you've just flip-flopped it back round. So in this circumstance here, there's no pi shift, but there is a pi shift. And so as a result, we need to be careful to see whether or not this value is going to be constructive or destructive based on any pi shifts that occurred. So we might put that as a clear kind of thought. If a pi shift occurs, then 2d is equal to m lambda equals destructive. 2d equals m plus a half lambda is constructive. Okay, so that is a nice little handy kind of cheat sheet, just to get you thinking about what happens if one pi shift occurs, then that is destructive and that is constructive, which does often happen. If you think about a bubble, for example, a bubble of water, that you might blow, the bubble is a layer of water mixed with washing up liquid, and when the light passes through it, it then passes back into air. So you have pretty much got a air to, probably not oil, but other higher refractive index back to air. So you are probably going to get a pi shift with bubbles, very specifically. So that is where those equations can slightly differ. But however, we're not done. These equations aren't complete, because this wavelength here is the wavelength of light in this medium here, because it's got to be how this distance is related to this wavelength to create the path difference. So we've got to maybe look at this from the point of view as it's very unlikely you would be given the wavelength in here. That is very unlikely that you'll be given that. More than likely, you'd be given the wavelength out there of the light coming into the film. And so as a result, we need to rewrite this equation slightly to make sense for this lambda, not for this one. So if you like, we can actually write this as lambda b and lambda a. This is lambda b, and this is lambda b as well. So like I said, there's a bit of a problem in the fact that we cannot accept this one right here. It might be something slightly different. So let's have a look and see if we can explain that out. So we've already written those equations as 2d equals m lambda b, and we'll actually stick with this equation. We'll do the destructive one or the constructive based on a pi shift here in a second. So we want to rewrite this equation in terms of the lambda outside of the thin film, not inside. So we need to have a look at what we can do. So I said before that this was n equals 1 and this was n equals 1.3. Now, let's have a think. How is lambda A related to lambda B in this circumstance? Well, it's going to be affected because of the refractive index. Now, the refractive index is an indicator of how the speed of light changes when going from one medium to another. So, for example, in this circumstance here, n equals 1.3 lets us know that because n is equal to c, which is the speed of light in air, because this is in air, over v. And we'll actually say that that's v in B because that's material B. So that's the value there. So this is, we can call this NB just for completeness so you can see which ones I'm talking about here. Well, we can also then draw a relationship. Well, what is the relationship between V and lambda? Well, V is equal to F lambda. So, and you should maybe remember from refraction that when refraction occurs, frequency stays constant, but the wavelength will decrease in this circumstance when it goes from a less dense to a more dense medium because the speed will decrease. And because we can then say that V is proportional to lambda. Well, look here, we can also say that VB is equal to C over NB. Well, if we follow this through, we can then say that V is proportional to 1 over N, and since V is proportional to lambda, we can then quite happily say that lambda B is proportional to N, 1 over NB. Which is interesting because what that means is that when we have decreased the velocity, when we increase that, we decrease the velocity. I'll do that in a different color to just make that really clear. When we increase the refractive index, we decrease the velocity. When I decrease the velocity, I decrease the wavelength. And so as a result, what's happened here is we know that lambda B has been decreased by a factor of NB. Well, we can then throw that into the equation. We can actually say that lambda A, that lambda A there, is going to be equal to, lambda B is going to be equal to lambda A over NB, because that's how much the wavelength has changed by. So lambda B is equal to lambda A over NB. And so we can then put this up here. We can change this equation. 2D is equal to M lambda A over NB. Sorry, it should be little n, refractive index. And so there we are. We can then reiterate this equation as 2dn is equal to m lambda a. Should be a little a. Let me just rewrite that out so it looks a bit better. 2dn equals m lambda a. Like that. And so now we have our new equation for destructive interference when there is a pi shift, which, like we said, there normally will be. And we can do the same thing for the constructive one. So constructive is going to be 2dn equals m plus a half lambda a, where the lambda a is the lambda of the light coming in. So if you're looking at all this and you're going, oh, what is going on there? Don't worry too much about what I've done here. All you need to appreciate is the fact that to get the value of lambda a into this equation, we've had to divide it by the n of the material that the light is passing into to get what the wavelength is out here. And we've done that for each equation. And that gives us two final equations that we can utilize. So I know this has been quite a long video, but it's just showing you where these equations come from and how they are used to decide whether or not you have destructive or constructive interference from a thin film.